Overview of Book 1. Book 1 is a modern exposition of classical mechanics, including chaos theory, and including ties to later theoretical developments as well. The exposition consists, throughout, of the presentation of interesting problems with many solved, the others left for the reader. The problems are drawn from classical mechanics, CM, and mathematics courses taken at Caltech, Oxford, and the University of Wisconsin. The courses range from undergraduate level to advanced graduate level. The courses had a rich and sophisticated selection of textbook and reference material, as you might expect, and those reference texts are similarly drawn on here. Those classical mechanics texts, listed by author, include Landau and Lifshitz, Goldstein, Fetter and Waleka, Percival and Richards, Arnold O.D., Arnold C.M., Woodhouse and Bender and Orzag. Notice how the first Arnold reference and the Bender and Orzag reference involve textbooks focused on ordinary differential equations, ODEs. Likewise, an analysis of the excellent and rapid exposition by Landau and Lifshitz reveals that it partly progresses through the material by going through ODEs of increasing complexity, corresponding to more complicated pendulum motion, for example, such as by adding a frictional force. This strong alignment with the underlying mathematics of ODEs is continued in this exposition, so much so that an appendix is provided for a quick review of ODEs from the applied mathematics perspective.
Particle dynamics, with and without forces, are described, with all arriving at descriptions with chaotic motion, with chaos described in the latter half of Book 1. Universally it is found that systems transitioning to chaotic behavior do so with a remarkable period doubling process, and this will be described both mathematically and with computer results. In the analysis of such dynamical systems we will find that periodic physical systems can be described in terms of repeated mappings, e.g., classic dynamic mappings, and when described in this way the transition to chaos is made much more mathematically evident, as will be shown. The familiar Mandelbrot set is generated by such a repeated mapping, where its edge of chaos is defined by the fractal boundary of the classic Mandelbrot image. Properties of the classic Mandelbrot set will be relevant to the physics discussed in Book 1 and Book 7, including the property that the fractal boundary has a fractal dimension of 2. The fractal dimension of the boundary can be between 1 and 2. To get equal to 2 is special. With the Mandelbrot set we also recover the well-studied constants associated with the universal Feigenbaum constants. In the Mandelbrot set we can clearly see the fundamental constant for maximum perturbation that is at maximum antiphase, negative, with magnitude c sub infinity, where the same results hold for a family of basic formulations, for a variety of Lagrangian formulations, for example.
From the Lagrangian variational formulation of action for particle motion we will eventually define the path integral functional variational formulation involving that same Lagrangian to arrive at a quantum description for the non-relativistic quantum particle motion, described in detail in Book 4 and relativistic in Book 5. From the quantum description we arrive at the propagator formalism for describing dynamics. This exists in the classical formulation too, but typically is not used much in that context. Complex propagators will then be found to have ties to statistical mechanics and thermodynamics properties. Book 6. The ties to statistical mechanics are further emphasized when at the edge of chaos, but with the orbit motion still confined. This may be associated with an ergodic regime, thus an equilibrium and martingale regime, the existence of which can then be used at the start of Book 6 statistical mechanics and thermodynamics derivations with the existence of equilibria established at the outset. The existence of the familiar entropy measures are already indicated in the neuromanifold description, Book 3. Thus, together with equilibria, the Book 6 thermodynamics description is able to begin with a well-established foundation that is not claimed by fiat, rather claimed as a direct result of what has already been determined in the theory/experiment described in the previous books of the series.
Overview of Books 2 and 3. When moving from a theory of point particles to a theory of fields, there's not much discussion in the core physics books on fields in a general sense. It usually just directly jumps to the main field of relevance, electromagnetism, EM. If advanced, it may also cover general relativity, GR, as with reference 125. In what follows we will cover these topics, but we will also cover the more basic fields in 1, 2, and 3D, including fluid dynamics, as well as 4D Lorentzian field formulations for special relativity, the gauge field formulation, thus Yang-Mills covered in a classical context, and the GR geometric and gauge formulations. This establishes the foundation for the standard forces, and upon quantization, books 4 and 5 in the series, lays the foundation for the standard renormalizable forces, all but gravitation. The gravitational coupling constant G is a dimensionful coupling, not like with alpha and EM, and gravitation with manifold construct can be described as a gauge field construct, although not renormalizable. Gravitation, and associated geometry/manifolds, appears to relate to its own emergent structure, as will be discussed in Book 6. From the local Lorentzian geometry and Lorentzian field descriptions we also see the first of many examples where there is system information in the complexification of some parameter, here the time component. If the Lorentzian is shifted to complex time, this shifts it to being a Euclidean field, with formally well-defined convergence properties, as occurs in statistical mechanics. Complex time also shows deep connections between classical motion and associated Brownian motion, where random walk reveals pi. Thus, it should not be surprising that an emergent manifold may have complex structure such that there is also an emergent thermal manifold, possibly the neuromanifold described in Book 3 and the related partition functions examined in Book 6. Just like locally flat spacetime is a natural construct in GR, so too are optimization, learning, steps on a neuromanifold such that relative entropy is selected as a preferred measure, and from it Shannon entropy and Boltzmann's statistical entropy. Thus, the manifold construct appearing at Book 3 has far-reaching impact into the foundations of the thermodynamic and statistical mechanical theory described in Book 6.
Before we even get to the manifold/geometry complexities of GR, however, we have already established much with the EM field part of the theory. 1. From free EM without matter we get the speed of light c Lorentz invariance, and from that special relativity and locally flat spacetime. 2. From EM with matter we get the dimensionless coupling constant alpha. In going over field theories to describe matter, force fields, and radiation we first described the classical field theories, CFTs, of fluid mechanics, EM, and general relativity with many examples shown. This is then carried over to the quantum field theory QFT description in Book 5. A review of the core mathematical constructs employed in CFT and QFT is given in the appendix. Even as the mathematical physics approach grows in sophistication, we still obtain solutions via variational extrema. Thus, determining the evolution of the system from its variational optimum now becomes the focus of the effort. System propagation from one time to a later time can be described by a propagator. Although a propagator formulation is possible mathematically in classical mechanics, CM, and classical field theory, CF, which are shown, this is usually not done, in favor of simpler representations for the experimental application at hand. As we move to descriptions in the quantum realm, however, the use of the propagator formalism becomes typical, and when used in the path integral formulations we arrive at a compact formulation describing both the evolution and stationary phase solution at once.
In Book 2 the focus is on classical field theory and a fixed geometry. The main physical example is EM. In this setting alpha appears, for example, in the description of an electron-positron pair, F equals E squared divided by 4 pi epsilon A squared, for electron-positron distance A apart, where alpha appears as the coupling constant. Later, in quantum mechanics, QM, both modern and in the early Bohr model, we have that alpha equals open bracket E squared divided by 4 pi epsilon close bracket divided by CH over 2 pi. The appearance of alpha in these situations is occurring in bound systems. If we examine EM interactions that are unbound, on the other hand, such as with the Lorentz force F equals Q times E times V, here there arises no alpha parameter, nor with the early quantum mechanical analysis of such systems such as with Compton scattering. Thus, we see an early role for alpha, but only in bound systems, thus only in systems with convergent, perturbative expansions in system variables. In Book 3, Classical Field Theory with Dynamic Geometry, i.e. GR, we don't see alpha at all. Instead we see manifold constructs and the mathematics of differential geometry, and to some extent differential topology, and algebraic topology. Manifold constructs are entirely encapsulated in the math background given in Book 3 and the appendix there. An application in the area of neuromanifolds, see reference 24, shows the equivalent of a geodesic path in this setting is evolution involving minimum relative entropy steps. Similar to the description of a locally flat spacetime, we now have a description of entropy increasing/evolving according to minimum relative entropy.
General relativity, GR, stands apart from the other force fields. All the other force fields are part of an adjoint representation of the standard model vis-a-vis the stability subgroup U, 1, XSU, 2, LXSU, 3, the form of which is derivable from the chiral T one-sided products described in Book 7. The standard model is uniquely obtained in this process, and with no mention of GR. Keep in mind, however, that the adjoint representation has operation on some space, hyperspinorial in case of simple octonion right products, for example. The force due to gravity is that due to manifold curvature, where the manifold construct is possibly emergent on the space of operation. Thus, the origin of the GR force is entirely different, and it will not allow quantization like the other forces, nor will its singular solutions be resolvable via quantum physics alone, as with EM in Books 4 and 5, but will also need thermal physics, as will be described in Book 6. The existence of singular GR solutions, outside of specially symmetric cases, the classic black hole solutions, wasn't firmly established until the Penrose singularity theorem, awarded Nobel Prize in Physics for this in 2020. Some of this material is covered in Book 3 to show how the mathematical formalism shifts to differential topology methods to describe the singularities, with examples referencing the Hawking and Ellis classic and using Penrose diagrams. This, in turn, will come in handy when describing the classic FRW cosmologies with radiation and matter-dominated phases, using notes from Peebles. Peebles won the Nobel in Physics in 2019.
The GR development would be remiss if it didn't briefly delve into cosmological models, the classic FRW cosmologies in particular. With the GR tools developed, cosmological results are examined, starting with the entry of the cosmological constant into the formalism, a candidate for dark energy. Various observational data on galaxy rotations and universe simulations of galaxy cluster formation both indicate the existence of dark matter. This, then, means we have new matter, non-interacting except gravitationally, and this is actually consistent with the latest observational data on the muon G2 value, where the discrepancy between theory and experiment has grown to 4.2 standard deviations, where an extension in the standard model appears to be in the works. This is convenient as emanator theory, Book 7, predicts such an extension. We can thus arrive at field equations for EM, GR, and Yang-Mills gauge fields strong and weak. We can obtain wave and vortex phenomena, as hinted in fluid dynamics. We show the classical instability for atomic matter, classical EM instability, and classical gravitational instability, leading to black hole formation with singularity. From Lagrangian formulations we can then arrive at a QFT formulation, Book 5. The QFT formulation completes the QM, Book 4, cure of non-relativistic atomic instability, with the cure of the fully relativistic atomic description of the radiative collapse instability. Introduction of QFT also leads to new instability or infinities, but these can be eliminated by renormalization for the EM and electroweak formulations, and the Yang-Mills strong formulation, but not the GR, gauge, formulation. The current theoretical formulation in modern physics has one glaring gap, therefore, a quantum theory of gravitation. Perhaps this is not a missing element, however, if geometry/GR is a derivative phenomenon, like the field of statistical mechanics and thermodynamics appeared as derivative phenomenon when the complexified quantum propagator gives rise to a real, quantum, partition function. The hint of a deeper emanator theory suggests emergent structures of geometry and thermodynamics are arrived at in the process of emanation, with the information emanated being that of the renormalizable quantum matter fields. In Book 7 a precise mathematical meaning will be found for describing maximal information emanation.
Overview of Book 4. By 1834, with Hamilton's principle, there was a strong foundation for what is now called classical mechanics. By 1905, with Einstein's publication on the photoelectric effect, the rules of classical mechanics were being superseded by the new rules of quantum mechanics. The earliest appearance of quantum mechanics, however, began with the various observations of quantization of light, starting with the strange occurrence of spectral lines for hydrogen. The hydrogen spectrum was made even stranger by a precise fit to a succinct empirical formula by Balmer in 1885. This is the beginning of an amazing period of discovery. The developments of QM from introductory to advanced roughly follows that history. The early phase of discovery for quantum mechanics moved into the modern quantum mechanics formalism with the discovery of Heisenberg of the successful application of matrix mechanics and the resultant uncertainty principle, 1925. In 1926, Schrödinger showed that the problem of finding a diagonal Hamiltonian matrix in the Heisenberg's mechanics is equivalent to finding wave function solutions to his wave equation. An interpretation of the wave function was then clarified in 1927 by Born. Dirac developed a manifestly relativistic formalism for the wave function and wave equation for fermionic matter, 1928. An axiomatic reformulation of quantum mechanics was then given by Dirac, 1930, laying the foundation for much of modern quantum notation and for critical issues such as self-adjointness. Dirac then described a formulation of a quantum propagation path, with quantum propagator having the familiar phase factor involving the action, in his paper The Lagrangian in Quantum Mechanics in 1933. In essence, Dirac had obtained a single path, in what would eventually be generalized by Feynman to all paths with the invention of the path integral formalism, 1942 and 1948. The equivalence of a quantum mechanical formulation in terms of path integrals and the Schrödinger formalism was shown by Feynman in 1948.
In a path integral description, the quantum mixture state, semi-classical physics, and classical trajectories are all given by the stationary phase-dominated component. A stationary phase solution that is dominated by a single path is typical for a classical system. Thus, variational methods are fundamental to analysis of physical systems, whether it be in the form of Lagrangian and Hamiltonian analysis, or in various equivalent integral formulations. Feynman's discovery of the path integral formalism wasn't solely based on the prior work of Dirac, 1933, although by appending that paper to his PhD thesis, 1946, its importance was clearly emphasized. Feynman also benefited from work going as far back as Laplace for selection process based on highly oscillatory integral constructions that self-select for their stationary phase component. This branch of mathematics eventually became associated with Laplace's method of steepest descents, then to the work of Stokes and Lord Kelvin, then to the work of Erdős, 1953. Feynman and others then invented quantum field theory for electromagnetism, QED, during 1946 to 1949, more on this later. Extension to electroweak occurred in 1959, and to QCD in 1973, and to the Standard Model, in 1973 to 1975. Thus, the impact of the path integral revolution in quantum physics was felt well into the 1970s, but this was only the beginning. At their inception, path integrals were examined by Norbert Wiener, with the introduction of the Wiener integral, for solving problems in statistical mechanics in diffusion and Brownian motion. In the 1970s, this led to what is now known as the grand synthesis, which unified quantum field theory, QFT, and statistical field theory, SFT, of a fluctuating field near a second-order phase transition, and where use of renormalization group methods enabled significant advances from QFT to be carried over to SFT.
The grand synthesis is one of many instances to come where we see analytic continuation of a constant or a parameter giving rise to familiar physics in the thermodynamic and statistical mechanics domains, showing a deeper connection, still not fully understood, see Book 7. The Schrödinger equation, for example, can be seen to be a diffusion equation with an imaginary diffusion constant. Likewise, the path integral can be seen to be an analytic continuation of the method for summing up all possible random walks. In Book 4, we also carefully examine the closest gravitational equivalent to the hydrogenic atom, dust shell collapse. What results is an incomplete formulation due to boundary conditions, where to get the time choice you must input that time choice. No specific choice of time is indicated to avoid infall collapse. The results, however, can show stability and consistency in a full thermal quantum gravity description where analyticity is employed. Success in this way, and not others, suggests possible fundamental role of analyticity and thermality, Books 6 and 7, and also suggests that thermal quantum gravity TQG may exist or be well formulatable, while quantum gravity QG generally might not exist. These results, shown in Book 6, provide the lead-in to the Book 7 discussion on emanator theory, where core concepts in Books 1 to 6 that tie to emanator theory are brought together in a new theoretical synthesis.